So is that showing up now?
Looks good.
Okay, we'll get underway then. So this is David Quast, and I am the director with Cowtown Best. And before I was the director in other roles, I was actually a coach for 5 years. So I have been through the mud in all of this. And again, this is primarily aimed at those of you who are new at this, but I'm certain that there's a couple things that you'll pick up as well. So moving on. We're going to try to move on. There we go. So purpose. The focus of this presentation is about increasing the odds that you will have a successful team. And then I put there, what is success? For some teams, it is going to be winning, winning all the awards. For some of you, your focus may be on getting the students to learn as much as they can, which of course, sometimes failure can be a powerful learning experience. And then also I have participation. Participation is simply exposing our students to some of these STEM activities. And then I put there, the key to being successful is having a plan. And the overarching challenge to best of the competition is the time. So normally it's a 6-week time frame, which goes by in the blink of an eye. This year, due to COVID, we will be having a 8-week season. So you have an additional 2 weeks, but you still have to keep on track, or you'll just simply run out of time. So the outline here, I have kind of a season walkthrough, and then followed by what I consider some must-do tasks. So for the season walkthrough, try to do as much as we can pre-kickoff. So review the engineering process. So this would be things like go over brainstorming activities, go over process as far as, design, build, test. So those types of activities. I also have here, create engineering design template. And this is something actually a little bit new to me, but I have an example here from Martin High School that they actually use for each component of their design, and to help document how they got from point A to point B, which will help later on when you have to write your engineering notebook. So I'm not going to go through that in detail, but that's just left there as a reference. Other things you can do is review past competitions and designs. And there's actually, if you go to the BRI national website, you can actually go look at old games and whatnot. So that can be a good activity. And then also important is lining up help, parents, mentors, alumni. And also for some of you, you'll need to line up a place where you'll be able to do robot construction. And the next thing I have is pre-kickoff activity is shop training and safety. A lot of our students don't really have any kind of experience around a drill press or a saw and whatnot. They just haven't really constructed anything. Then I have assign all team positions. And this can vary a little bit depending on, do you really know the capabilities of your students? If you're a new team, you may or may not know the students coming into your team. If you're an established team, something like this would be easier. And again, I'm not going to talk through all this, but this would, again, this is an example from Martin High School, but this would give you ideas about what kind of positions you may consider assigning. If you really don't know the capability of your students and/or you're pretty small such that, the students will actually have to, serve many roles, that's not an essential thing, but you will end up assigning positions to your team, although it may not happen actually before the kickoff event. And then I have plan meeting / workday schedule. This is pretty important. I have a couple different examples just to give you an idea of the time that's involved. So from the last year that I coached in 2007, I spent about 95 hours meeting with my team. And so that's the entire process as far as, brainstorming and planning and doing the actual build and testing and practicing. What this does not have the hours for is the academic portion, like the writing of the engineering notebook or preparation for the marketing presentation. We also normally have something, an exhibit, but that portion of the competition we will not be doing this year, again, to restrictions around due to COVID. So, kind of a heads up that this can take up quite a bit of time. And I would say even for the simplest of robots, I would think it's probably going to take at least 40 hours, even to get a very simple robot. I have another example here. And this is just taken from Alabama Best. And their estimates are from, you can see there, from 78 hours to 124 hours. So again, quite a bit of time involved. So for those of you that are restricted on time, hopefully students would perhaps be able to do, take portions home and work at home with it. But depending on your situation, just need to think through that. And then here's my recommendation is after the kickoff meeting is to immediately start your activity. And so for my team, when I was doing it, we would hand out copies of the game's specific rules immediately following the game, although that was back in the day, they actually handed out hard copies, and now we just give you links. But we would, even if they didn't, actually what we would do is we would get hard copies and we'd go print them off over at Kinko's or whatever, and actually hand out a paper copy to each team member. So sometimes that's helps having something in their hand. And then we would talk through the game and possible strategies. And we would try to define what we thought the robot was going to have to do and things that we thought would be a good idea to have it do. And then per those initial meetings, we didn't actually do any problem solving. We were mostly trying to make sure that we were clear on the rules and the problems that needed to be solved. So more about problem definition at that time as opposed to problem solving. And then I threw this in here. It says, yeah, an okay idea done well is much better than a great idea done poorly. The students typically will want to do all of the game elements, and they can bite off more than they can chew. And we'll talk a little bit more about that later, especially as a new team. I would have your students focused on being able to score at least one item, because a typical best game is going to have multiple different game objects that can be scored. And so for a new team, simply be able to, get a moving robot that can score any points is very much a successful first-year team. Continuing on, brainstorming, I said adult-led will go faster, and then also record everything, have students take notes, take pictures of your whiteboard or whatever you're working on. If you have more experienced students, having a experienced student lead brainstorming is actually a good activity for them. So it'll kind of depends on the makeup of your team. And then the next step, the students are giving various ideas, is try to spend enough time such that the other students understand the idea that's being presented. And then it's also okay to evaluate on the fly there, is the idea feasible? For example, coming up with an electromagnet is probably not feasible given the kit materials we give you. So that's can delve into that a little bit. And then discuss the pros and cons of each idea. And then often a technique we would use, say we have 20 different ideas that we're voting on, is, I might give each student 5 votes, and, they can put all their votes on one, or they can spread them out. You can come up with various rules. But in particular, if you have a lot of ideas, you're going to want to whittle those down a little bit before you evaluate more in depth. And normally what I would do for evaluating more in depth was come up with some sort of decision matrix. And I'll show you an example here in a minute. And I just put in the comment, make sure that something related to easy fabrication is accounted for. Because if everything they come up with is difficult to fabricate, that'll eat up all your time. So here's an example that I did for, looks like for my 2007 season. And in this case, we had multi-voted down to 4 particular ideas. And then we were trying to rank those from best to worst. on the various criteria. And this particular game, the game items were bottles and boxes. So we tried to determine how good we thought that particular idea would be at collecting boxes, how good that particular idea would be at collecting bottles. Likewise, we had a weighting for precision and maximum speed, or I should say minimum precision. So essentially, minimum precision means how easy is it to drive. Some robots require, very precise hand movements, and they can be very difficult to drive. And obviously, maximum speed is good. For a lot of games, your robot can spend a fair amount of time simply driving from point A to point B out there on the game field. Minimum movement, again, kind of related to speed, less movements faster. And we rated releasing items and simple and robust, having to do with the robot not being very fragile. So in this case, the scoop with notches came out ahead of the other ideas, and that's the route that we took for that particular year. And I have another example here. I will not go into that in detail like I did with the last one. But again, coming up with different, in this case, they were evaluating 6 different design ideas. And then they got this list over here of the evaluation points that they were coming up with. And 2, I'm not sure if it says it here, on some of these, you can actually kind of, give it a higher weighting because it's more important. So, it could be that all the items in column G, you multiply by 2 because you considered that the items in G are more important, for example. Okay, moving on. Forming build teams. And as the coach, you're trying to consider your students' technical skill as well as their leadership abilities. And again, some of this, if you already know your students, you might have actually selected some of these positions beforehand. And very typically, in fact, I saw that Martin's example followed this. Normally, I would have 3 build teams for the robot. One team that would build the base, one that would build an arm, and then one that would build a end effector or grabber or such. So most of the robots can be broken into 3 different assemblies, such that you can be working on multiple parts at the same time. Then this is pretty important, is to build mock-ups or partial assemblies. So proof of concept. So I say prototyping. So is it going to work? And I put here, cardboard is your friend. So I'll go to this here. And this also kind of gets into your coaching philosophy too. And I say here, yeah, my advice about giving advice. So my 2 students that were working on these particular items, I multiple times told them, hey, you should test one of those before you continue on. But they chose not to listen to me. And so they built a big pile of these. I think there's about 12 of them there. And the construction was not simple. They spent a lot of time doing this. And then I put there that, yeah, they threw all of those away. They did not work. And there's the final design, which if you look at, yeah, this is, they created a forming tool to form all these pieces of PVC plastic. And then all these blocks with a fairly precise dimension that were supposed to fit into a hole. And then there's a dowel sticking out of the block and some pieces of inner tube on there. This was, yeah, to pick up handkerchiefs. And the final design to build each one of these, they probably only spent 25% of their time to build one of these as opposed to one of the previous ones. And here's evolution on a different robot. So for proof of concept, and I guess this, does my mouse show up, guys? Anyone?
I'm not seeing your mouse.
Okay. I'm not sure how to make it appear. So I'll just, oh, hey, what's that? Laser pointer. Oh, there we go. So
Yes,
this,
nice.
our proof of concept here was pretty simple with, you know, some made out of cardboard and some scrap pieces of wood. And based on that, we figured out that our little flapper design was going to work. So the next iteration over here had like a plastic lip on it. Then we had a fork in it, and the fork was to pick up these bottles over here. The flapper would pick up the square boxes. And so we started initially practicing with this design here, and that evolved into this next design. And I think this design here is where we competed at the local level. And then between the local level and the state level, we actually refined the design to make it better. So that shows you kind of a evolution from mock-up to the final design. It's not going back with my, not sure how to get out of my laser pointer thing. Okay, let's see if okay, I can get back now. And I put, yeah, fabrication refinement. I said, yeah, maybe you can make it out of cardboard. Again, actually, if you can make something out of cardboard, often it's adequate. And of course, assembling with cardboard is quite quick. Okay, going into the building of the robot. And even you should have been doing mock-ups and prototypes before you're building final details. But even for some of the smaller parts, I would always have the students explain what they're going to build and draw it before I would let them proceed. I don't know if you want to comment here, Danny. Danny Kay is joining us from, he's used to be a mentor over at Martin High School. And would you pretty much have him prototype every bit and piece, or?
Absolutely. I mean, one of the things I was going to suggest is that you guard the official materials carefully. Otherwise, they will pick all the stuff you can't replace, use it, and then you'll be left scrambling to try to figure out how to get more. So they always had to prove it in cardboard before we let them go on to anything.
Okay. And I wholeheartedly approve of that. And I didn't have too much problems with running out of materials, but I also had a smaller team. Next bullet point here, encourage simple design. And normally I would simply do this by asking questions. So I have an example here of this. It was a basket that was, they cut metal strips and then wove a nylon string basket. And I'm not sure how many hours they spent on that, but a lot. And I did not stop them, but in retrospect, I probably would have asked more questions. That's what I'll say about that, because they could have made something probably out of cardboard, and if it needed extra durability, they could have put a piece of wood or plastic or metal just at the mouth of the basket rather than constructing this elaborate thing. And then Danny also had a suggestion that they would always ask, not only about making it simpler, but also making it lighter. Often teams will run into issues with weight. There's kind of two things: is the lighter your robot is, the faster it can be. And then there's also the aspect of simply being overweight. You have a maximum weight limit of 24 pounds. So you need to stay under that. And some teams ended up drilling a whole bunch of holes in their robot to make their, to get it under 24 pounds. So sometimes it ends up looking like Swiss cheese at the end. I had this comment here about completing a bad component design may be the best path forward. Reason being is it can allow overall team progress. So I have an example here. This is the same one I was showing, the evolution of the flapper arm. So we had gotten to this point. Actually, before we even quite finished this, we had figured out that it was not going to work. So, but I wanted to get the team practicing. So this arm that wasn't going to work behaved very much like the one that the final design. So I had the team finish this at the same time. They're already starting on the next arm. So this arm was kind of designed, it had a rotational point about the center of this pulley. And then here's the final design. It's more like a crane. So the arm was kind of hinged in the middle and would flip out. So again, strategy about making best progress. And then my last point there, be directive when appropriate, and about, don't allow your students to remain stuck. And then actually, if you feel like you're kind of stuck as a coach, please contact us, contact me, and we will get you help. And then with respect to the students, to get them unstuck, I would ask them questions. And then if they're having difficulties coming up with a mechanism, I would help provide them with examples, like, real world mechanisms like, okay, how does a dump truck work? How does a forklift work? How does, anyway, some physical mechanism that they'll be familiar with to, think about, okay, what are the different ways I can solve this? Recovery. And yes, this happens all the time. So if a design doesn't work, or if you're falling behind schedule, the students aren't necessarily going to recognize this before you, probably won't recognize this before you. So in part, if you already are suspect about a design that they're pursuing, is even up front, you can kind of, okay, what is your plan B if this doesn't work? So already get them thinking about alternatives. As far as falling behind, I put the item there, what can be tossed overboard? So for example, perhaps you had a design that was going to be able to handle 3 different game pieces. Well, maybe you figure out how to, if you can save time, you reduce the number of items that the robot can handle. And then the last thing is, can additional work time be scheduled? So I work with a private school when I was coaching my son's team, so I had a lot of flexibility on that. So I think I only did, maybe 2 all-nighters over a 5-year period. So, but yeah, we tried to avoid that sort of thing. Practice. And some suggestions there are, if you have an old robot, and it doesn't even necessarily have to be a best robot, is modify it for practice. So in the past, I've even taken like a remote control car, like a toy that you would get at Walmart, and modify it. Especially if your students are new to driving these sorts of things around, it helps them, the controls are opposite when you're driving at yourself, but it helps develop the hand-eye coordination, even if they're not practicing on the actual robot, if you can give them something similar. Also, when you're practicing, you should be making a list of items to fix and then rank them. So typically what I would do there is, we had the list and we would rank them as, high, medium, low in terms of priority. And then as far as fixes and refinements, and we would try to schedule those such that we wouldn't affect practicing. So typically for my students, we try to practice after school. And then later in the evening, we would do work on the robot. And then I have that last item there, practice everything. And I have this particular example. We call it robot on a stick. And the one, so this is robots on a cantilever 10-foot pole. It's got a, well, cantilevered, it's got a fulcrum, it's hinged, it's like a teeter-totter. And what we had not practiced is putting the robot onto this 10-foot pole. And when we got to the actual competition, some of the students just had a bear of a time getting it on to that pole. So something we, lessons learned, we should have practiced, we just didn't think of it. So, and it could be, you don't have to practice, every item every time, but you do want to make sure you practice all aspects of the game such that you don't get surprised. Okay, I'm ready for the next slide. For the actual competition, recommend that you have a checklist both for pre-match and post-match. And, that may be, it can be various things. Like for some of the robots we built, we would make sure that certain screws were tight. Certain screws would tend to loosen up perhaps. So part of our checklist would be, make sure these screws are tight, make sure the battery's plugged in. Can be some pretty simple things. do you want to add any of that to that, Danny? I'm not sure. I never had a post-match checklist. What would you have, for example, on a post-match checklist?
Post-match was usually making sure the batteries are charged or heading to the charger, and
Okay.
just making sure everything was basically, it was mostly the pre-match one done again, just in case something needed to be fixed that broke during that match. We wouldn't be scrambling
Ah,
pre-match because sometimes there's an hour between matches and stuff like that.
yeah, yeah. Okay, and next item there, if you have a design that you know breaks things, if possible, you can have replacement parts that if it gets broken, you can just swap it out. And I put the in parentheses there within kit limitations, because your robot plus all your spares, you cannot exceed the amount of materials that we gave you in your kit. So even if you do something like that, there is that limitation. And then I have the suggestion that you have a specific person assigned to charge the batteries on your team. Then you avoid the issue of one guy thinking the other guy did it and no one did it. So, and then it's very sad when your batteries die. So I have scout the other teams. And in particular, what I'm referring there to is when the other teams are out on the game field, is how does your team strategy hold up? Is if you have a strategy that's very specific to the particular path your robot's going to drive, the particular items it's going to get first, is there another team out there that's going to interfere with your strategy? And if that's the case, you probably need to come up with an alternate strategy. So that's if your robot is pretty generic in terms of the sequence of events that it does things or the items it can get, that's not as important. And also this year, it's not important at all, since each of you will be playing independently from any other team. So not an issue at all per this year. Must do items. So I put get the actual game pieces. This is the only way to verify the behavior between the game pieces and the robot. And I have a couple of examples here. So I think this was Mission to the Hubble was a particular game. So it was using quart paint cans, and on those, some of the cans were empty and some of the cans had a cabinetry, a specific cabinetry knob on them. So, the interface with the robot was very specific, such that you wanted to go purchase these items. And sometimes at the hub, sometimes we would hand out some of these specific items to the teams if we had extras at the hub level, in particular if they were hard to find or hard to get. Here was this item, the top on the bottle. The supplier ran out of them, so we were not able to obtain them. So we had to use a kind of a mock-up of the bottle top. And unfortunately, it behaved quite a bit differently in our robot. So when we got to the actual competition, the bottle kept jamming in our robot. Now, fortunately, we found this out a week. Well, I said we found out at the competition. We found out at the practice event that was a week prior to the competition. So we ended up having to do a little bit of scrambling to modify our robot such that we were able to get the robot in and out of our capture device. Um, then I put build a portion of the game field, and essential for practicing, and small details on the field can prove to be very significant. Again, I'll have a couple examples here. So here's my living room. And again, we just build portions of the field that were significant. This particular robot the robot didn't actually move. It was affixed out in the field. Here's an example of something we built up the practice field, but we didn't put in, there's little metal nuts in each of these bays that would make electrical contact with the can. And we didn't have those in our practice field. And what we found out is, we were thinking, hey, we don't need electronics on our practice field, but these little nuts interfered with us sliding the can into these bays. So we had to change our technique to get those cans into there. So again, we found out a week before the competition, and we were able to accommodate that change, but we were not as prepared as we wanted to be. So there's a practice field out on my driveway. That's that 10-foot pole thing. 1 year, a parent built an entire field, all 4 quadrants. So that's something in particular you can recruit your parents for. It's perfectly fine for your mentors and your parents to build portions of the robot field for practice. That's a good way to put them to use because they can't build parts for the robot. This particular practice field, again, portions, this low portion was actually in the real game field was 12 inches high, but we would actually, at one point, we would stop the timer. In fact, here I'll get the laser pointer. Hopefully I'll be able to get rid of it again. So we would drive our robot up, collect bottles, and when we got to here, we would stop the timer. Someone would go over and lift the robot onto this higher portion, such that this higher portion was at the actual level of the game playing field, such that we could practice driving down this ramp on the far side, which was an essential element of, I didn't get rid of it again. Here are options. Okay, got rid of it. Oh, I think I have one thing. I missed one item, one more slide. Because here I have that comment, Danny, beware of paint. This was a mining game, and we got a bucket of coal there. And one of the teams, they had not painted this ore bucket. And so unpainted wood tends to have lower friction. So their robot worked fine with their practice bin that was not painted, it was bare wood. But when they got to the actual field, the painted bin was getting stuck in their robot. So something to pay attention with when you're looking at the construction notes for a field. Some items must be painted on the field and other items are optional. So the items that are optional, you want to make sure that you're prepared for either. Surface could be painted or unpainted. And you can also, check with with us to find out, hey, we're going to be painting that particular item. This year, of course, since we're a classroom event, you each will be building your independent fields. And I'm not I don't believe any paint is specified this year. It may be optional, but again, this will be something that you're pretty much under control of this year. Must do items, and I have a complete functioning robot by mall day. So normally that would be the week before the competition. And that will leave a full week to practice and find the correct problems. And that is, I put invaluable, it is essential. Now, was my team finishing the robot the night before the game? Yes, a couple times, and consequently, they didn't do very well. So time to, if you want to do well at the game, you just have to have the practice time. In fact, often we'll see that some teams improve a great deal on competition day between their first match and their last match, simply because they're practicing in real time out on the field. Here were some of my personal milestones for the team. So typically week one, right after the kickoff, we would go through defining the problem. And by the end of that week, our goal was to have a specific design selected. I think talking to Danny over at Martin, they would actually try to have what I would have at week 3 is to have a drivable base. So for me, I'd like to, during week 2, no later than week 3, actually have a functioning drivable base. So, and it could be even that that's going to be modified, but again, actually getting to the point where you have something to drive around and to be able to start programming is helpful. And then, as I mentioned before, week 5, have a fully functioning and complete robot. And I guess even this is probably, even though you have 8 weeks, I would try to, if you can spend 3 weeks practicing, that's even better. Design tips. First one doesn't really affect you, but I said assume robot to robot contact if you share the same field area, which is the highest percentage of the time that will be the case. And so what happens is if your robot's fragile, something's going to break. It's invariable that you'll run into other robots, not always on purpose. Some of the students are not in great control over their robot, so it's not always malicious, but again, there will be robot to robot contact. I put encourage fail-safe design features, belt suspenders. I put their design out single point failures. So an example would be the wheel hubs that my team produced. We would have it would both have a clamping mechanism and a set screw mechanism. So the idea of not having a single point failure is any single item can fail, but the robot and the mechanism itself does not fail. So you're not always able to do that, but certainly I would encourage your students to kind of point something out and go, okay, if this screw breaks, what happens? And get them to think through, okay, maybe I could add this, and then that screw is not, the entire robot's not dependent on one screw. Also avoid a design that stalls out a motor that will tend to sap your battery. And in the worst worst case, it may actually burn up some of your electrical components. And then I put use standard designs when possible. I put wheel hubs, wheel design couplings, servo mounts, potentiometer mount. So actually, we do give you in your kit some hubs that can be used as wheel hubs. They're not very large, not very robust, but then, you know, at least you do not, it's not a must that you construct some, but if you want hubs that are robust, you'll need to actually build those yourself. Wheel design, typically teams that have been around for a few years, they kind of have a go-to wheel design. Couplings, again, we give you a couple of shaft couplings in your kit, but they're not necessarily that robust. And then servo mounts, again, most teams over time will kind of have standard ways that they'll mount a servo. And not a lot of folks use the potentiometer, but again, these are things that, you know, you don't need to reinvent the wheel every year on some simple items. Okay, that is the entirety of my presentation.